Hello, good morning, everyone. My name is Mahesha Manjunatha Pujari, and welcome to the sixth day of the GAN program, Next Generation Sustainable Alternative Proteins for Food, Fundamentals and Technological Innovations. So, in the first session, we're going to talk more about how do we use certain treatments to improve the techno-functional properties of proteins. Okay, food is never a one type of matrix, right? Just to give a generic idea here, sometimes we need a food that is colloidal, let's say milk, right? It should be watery. Sometimes we need milk that is kind of a soft and like let's say yogurt. Sometimes we need food which is little bit soft but little bit hard, let's say chicken breast, right? Sometimes we need foaming properties just to have it on your upper lip, I don't know. So we need something, right? And sometimes we need really hard thing just to chew, so to feel it to feel happy. So we need food in a different ways, but that all properties does not come with one plant proteins, let's say. We need to change so that it becomes a better forming protein with the better forming properties, for example. And I also refresh this again and again. I'll bring this picture on your head just to show that all the functional properties are related to structure of the protein. Structure is very important. Structure determines how protein binds to water. Structure determines how protein interacts with another components to improve the functional properties. So structure is important. We talked about again 4 different levels of protein structure: primary, secondary, tertiary, and quaternary. All of them are important building the food structure, right? Food structure is maybe because of protein. Of course, carbohydrates and other things also play a role. Protein has a lot of role in developing food structure. Structure also determines texture. Texture is very important, right? Just to give this baking background. But we have been also discussing a lot about, okay, we can do many things, but they all come up with their own challenges. Just to summarize challenges, just to give a background for my next topic, we all knew that plant proteins or insect proteins, they might have a very high concentration of some of the amino acid, but not all. Lysines are low, tryptopans are low, methionines are low, depending on type of proteins, right? Except, and then taste, they bring it some grassy flavor. Sometimes plant proteins are bitter. Sometimes plant proteins what we call astringent. So these are the problems. And then these are the things we need to look after just to improve the techno-functional properties of alternative proteins: taste, texture, flavor, and all these things. We have discussed all these things in detail. It's just to refresh your memory. What do we need today, and why do we have to modify proteins? And another important thing I kept telling you when I started with alternative proteins, they are sustainable, they are beautiful, they are nice, but they are also complex, right? Compared to milk proteins, compared to meat proteins, they are highly complex. Again, plant proteins are not built for human beings in general. They were built for plants. So they are usually globular in nature, right? Most of the plant proteins are globular, storage proteins especially, globular in nature, and they have a poor solubility. But when you take, we were discussing about STS page in one of the classes. Somebody was mentioning that whatever I do, I get a smear, right? So smear is a problem. It's very complicated because we have too many different types of proteins in a plant matrix, right? They are slightly different, what we call isoforms and so on. You also have albumin, globulin, prolamines together. You know that albumin has something, a different property, prolamines have a different property, globulins have a different property. Now, if I get a plant protein isolate, it is a mixture of multiple proteins, and individual protein has an individual property. Do you agree? And now I'm selling it as an isolate to everybody, but my end user might be dissolving it in water. My other end user may be trying to make a yogurt out of it. My other end user trying to make an infant formula out of it, right? Everybody is working with a different application with the same initial content. But this is not an individual protein, it's a mixture now. So in different food, they start behaving differently, right? Because maybe in milk application, maybe water soluble globulins, albumins becomes more active. I don't know. In high salt containing food samples, maybe globulins becomes more active there. So it's actually a complex mixture. So that predicting the properties of plant proteins or alternative proteins in a final food matrix is very, very complicated compared to milk or other type of proteins. Remember this word, plant proteins are not alone. They always come with their friends and family members, right? And when you have friends, it's another story. When you have family members, another story. We start behaving differently, right? Like that, plant proteins behave differently when they are associated with something else. So that thing also you have to keep it in mind. Then again, plant proteins are very complex. They have a very different thermal properties. That means you take rapeseed protein as an example. It has, I have isolated rapeseed proteins. I have two proteins along with that. I will have cruciferin and I will have nepin, right? Nepin has a melting point, say, above 100 degrees Celsius. Cruciferin has a melting point, let's say, 80 degrees Celsius. Now I have, somebody sold me rapeseed protein isolate, okay? Somebody sold me rapeseed protein isolate. I have nepin and I have cruciferin in it. Nepin melts at 100 degrees Celsius or above 100 degrees Celsius. Cruciferin melts at about 80 degrees Celsius, right? Now, I was very happy. I really wanted to use it as a food ingredient, right? Then I will come. I'm trying to make, let's say, a sports beverage out of it, right? I'm trying to make a sports beverage out of it. I add, and it becomes super soluble. I'm super happy, okay? But the problem here is that we don't eat proteins as solution directly, because then FSSI will come, FDA will come, they will ask, what about bacteria in it, right? Is it safe to consume? Then you suddenly think, oh no, I don't drink it directly, I have to do pasteurization, right? Then you apply heat treatment. Now, what do you expect in heat treatment? Okay, pasteurization I do at 70 to 80 degrees Celsius and for a long period. Then what happens is that suddenly you start seeing a precipitate, right? And the precipitate is a weird precipitate, because if you look into the melting behavior here, cruciferin melts or denatures, melting is the wrong word to use, I'm sorry, denaturation is the right word. Cruciferin denatures at 80 degrees Celsius, right? Around 80 degrees Celsius. So what do we see here? Precipitate, mainly cruciferin. The supernatant will be nepin, right? Now again I got a problem. Can you see here? It was our individual pros in isolate, but at the end I get a product containing phase separation. I have a supernatant differently and a and a precipitate, and who will drink a drink containing different phases? Do we? Phase separation is one of the challenges in food industries. We don't want to have phase separation. Now you see, the rapeseed isolate was a single powder. Nobody told me it contains so many things. I thought I want to be a plant-based. Now these are the problems I will face. Now how do I get everything into solution? Right? Even after pasteurization, everything should be in the liquid phase in this particular application, let's say, right? And then I have to modify the protein. Does that make sense? So I don't have the problem of phase separation. Just to give a technical example how complicated this business is at the moment, right? We are right in here now, but we need to do a lot to get the real product out of it. Make sense? Here is just one example showing how the cowpea protein melting temperature is there, and that actually tells the denaturation temperature. That actually tells us a lot of information. That means, okay, if I know the denaturation temperature of a protein, now I know how stable is this protein in thermal treatment. Now I immediately understand this protein may be useful in this application, but not that application. Sometimes it's nice to denature proteins, yes? You do this heat-induced denaturation to get aggregates, right? Heat-induced aggregates. So sometimes it's important to do, sometimes no, we don't have to get an aggregate. So this knowledge is useful. What was this figure? It's again soybean globulins. You can see that they have a different denaturation temperature, but I have a same soy protein isolate containing two different proteins, two different properties, and I might have different properties in the end product. Okay. Now I also showed you this nice diagram. This was one of the nice diagrams they tried to compile how the solubility of different plant proteins look like with respect to pH, right? one of the take-home message in from this diagram was most of the plant protein, especially these globulins, right? They have pi between 4 to 6. You can see, right? They have a pi between 4 to 6. What do you mean by pi 4 to 6? What is the property? What happens at the pi? Protein precipitates. Not all proteins, globulins usually, they precipitate, right? Why? Because you have mostly high electrostatic interaction and they just precipitate, right? Precipitation, some cases is very important for extraction, for example. Precipitation is important. For aggregation, maybe precipitation is important, but some cases precipitation is not good. Why? Because let's say I would like to put this into some beverages, right? And the pH of that beverage is, let's say, 4, right? pH of the beverage is 4. What would happen if I use this protein? It precipitates. Do you agree? Now, this protein is not useful in this beverage. Please note that food fortunately have a very good pH range. They usually, most of the food, what is the pH range of most of the foods? Slightly acidic. So basically, if you take yogurt as an example, I don't know, pH is around 4, right? Some maybe fruit juices can come pH around 3, right? And then all the way depending, some alkaline foods are there. If you had a lot of garlic, for example, so pH can up to 8, right? This is the range where most, not I'm not telling every food, most of the food have a pH range, let's say 3 to 8. Now, if you would like to use plant proteins, and it's important to note whether that particular protein can be used, because if the pH is changing, the protein is changing the behavior, you might get precipitation or you might get higher solubility. You never know, right? So that is one of the things you have to keep it in mind, right? So it's important to bring proteins that is more applicable in the food which contains a particular pH range. Now, we also discussed about this figure. Globulins were really good. They have a sharp sharp precipitation. But albumins, usually they are crazy, right? They have a long solubility range. They don't want to precipitate. It's really good. In many cases, it's really good because plants usually food contains water. It becomes more soluble everywhere. We are so happy. But in some cases, we need to gelate the protein, right? Usually, how do we do gelation? How do we make cheese preparation? Rennet we add, or we do acid gelation, right? We add maybe citric acid to precipitate casein out of milk to separate casein and whey, right? And then the protein should have this property to gelate and to precipitate. Now, even if you add acid, I don't want to precipitate, then it might not be applicable in that particular application. Does that make sense? So depending on the pH, depending on their solubility, sometimes they are advantageous in some application. Some application they are disadvantageous. Maybe it's the wrong word. Maybe it's not applicable. Make sense? So now we need to change the properties of protein. Is it too boring for you? What I'm telling? You're getting the point, right? I'm trying to tell you why we have to modify. There's a lot of reasons why we need to modify plant proteins, okay? One more example here just to show, you can ignore this one for now, and you can see that digestibility of different proteins, right? We saw that usually soy is really good, highly digestible, but if you can look into this, I think these are insect, if I'm not wrong. So insect proteins, in this case at least, they were less digestible. Now, I mentioned in my previous case that insects are very sustainable. They produce very high amount of protein, extremely high amount of essential amino acid, even higher than plants, animals, but they are now less digestible. So if I want to use them as an ingredient in the future, I need to make them more digestible. How do? I have to modify proteins, right? And then again, we discussed about this. One of the biggest challenges today while selling the plant proteins, they are colored. Color is a problem. How do we remove the color? We need to modify proteins. So, just to summarize everything, I have given a background now. Protein modification is very necessary because protein modification changes the primary structure of the protein in some cases. In some cases, it changes the secondary, tertiary, and quaternary structure, and that will give you the desired techno-functional properties. Am I clear? Protein modification is nothing but, in principle, it's modification of the primary structure of the protein or secondary or tertiary or quaternary structure. One important thing I must tell you that when I use the protein modification, we don't modify every single amino acid. Keep that in mind. We don't modify every single amino acid in food application whenever I use the word protein modification. Sometimes we just open up it just by heating. Nothing has modified. Amino acids are stable, right? In some cases, I just modify lysine residues. In some cases, I just modify serine residues very selectively. So that will change the techno-functional properties. Are you aware of this particular point? Is it clear for you? Whenever I use the word protein modification, it's not the modification of every single amino acid. It's usually a minor modification when you compare the total amino acid composition, right? And that minor modification of protein perhaps changes the techno-functional properties. All right, so when we say protein modification, it is divided into three different types: physical modification, chemical modification, and enzymatic modification. I'm using the word protein modification here in the food science world. Is basically we are intentionally modifying the protein. Okay, protein modification also happens in our body. Okay, and that is not intentional. I mean, the body does it automatically, but in our case, we are intentionally modifying the proteins using physical treatment, chemical treatment, and biological treatment, let's say enzymes, and that will modify the protein to get the desired modification. Please note that we're intentionally modifying here. There is tons of different ways to modify proteins, and I copied this nice picture somebody summarized for me. And you can see that there is three different types of modification: physical, chemical, and biological, and other types of modification which cannot be categorized. No, you will have the slides at some point. There is people are trying every single thing to modify proteins, but I'm not having time to cover everything today. However, I will try to cover the most important things. Is that okay? The most common things we are following today. I promised to cover only chemical and enzymatic modification on the lectures, but when I was preparing slides, I realized that if I don't cover physical, it does not make sense because that's also used quite a lot. That was my mistake on the slide, but anyways, I'll try to mix them together, then I'll get you a better understanding. Is it okay? So let's start with the physical methods of modification. What do you mean by physical methods? It's basically we use physical things to modify protein. Light, radiations, heat, homogenization, anything else? Sonication, heating. Yes, exactly. We're not necessarily using chemicals or enzymes per se. However, using physical treatment, we are changing the structure of protein, and that will lead to change in the techno-functional property. That is a physical one. No chemicals are added intentionally. No chemicals are added intentionally. No enzymes are added. No microorganisms are added here. But because of physical treatment, chemical changes can happen. Is it clear? We are not adding chemicals. We are not adding any oxidizing agent. We are not adding any reducing agent here. However, because of physical treatment, chemical changes in food can happen, in proteins can happen. And that is the underlying phenomenon of physical treatment. Is it okay? I'll try to give some examples here. First one is heating. That's the most easiest thing to change protein property. When I use delta, delta means heat, okay, in chemistry. We all know that protein denatures when you do heat treatment. We have discussed that several times. And heat treatment is one of the common methods to get protein aggregates or gelates, right? That you have done it. Every protein has a different denaturation temperature that is unique, simply because, following of Niveta's and Asta's question here, they are made up of different types of bonds, different amount of hydrogen bonding, different amount of hydrophobic interaction. I use the word amount, it means the total number of bonds here, right? And that influences the stability. And sometime when you heat, proteins start denaturing slowly. They don't denature like this, right? It's a slow phenomenon. It's again, it's slow phenomenon. There's a lot of thermodynamics are involved here. It will denature slowly. And coming back to my previous example, or tryptophan example, right? Sometimes protein will have tryptophan inside, right? Hydrophobic components inside. You heat it slowly. What happens? Hydrophobic components comes out, because proteins are usually folded in a way that hydrophobics are inside. Why? Because it wants to interact with water, because world is made up of more water than hydrophobic substances. So it wants to interact with water, right? Cytoplasm contains more water than unwanted things, right? So basically, that's the reason why proteins are folded in such a way that hydrophilics are outside, hydrophobics are inside. Now you're heating, so they will open up, right? Then that hydrophobic moieties, amino acids, can interact with another hydrophobic moieties of another amino acid of another protein. Hydrophobic interaction, and the protein can precipitate. Sometimes they can gelate, and that's good for in some application. That's one of the things. The second thing is, coming back to her own question about disulfide bond, right? So basically, disulfide bonds and thiol groups are very, very crucial in creating protein structures. Extremely important, very common basic things what we do. Let's say gluten. Gluten has a stretchy structure because of this one, disulfides, right? The thiol groups will be, let's say, sometime buried, right? Thiol group is nothing but SH group. The protein will have a buried thiol group now, okay? Now, I will write one chemical reaction. This is thiol group plus a disulfide group, right? I'll write it as R1, R2, R3. When they come together, when there is little bit of pH, alkali condition usually, heat is not required, but heat will accelerate this reaction. So when small amount of heat is there, then we have a reaction called thiol disulfide exchange reaction. Have you heard about this one? Thiol disulfide exchange reaction. Now what happens is that this thiol group attacks the disulfide bond, and you create a new disulfide bond. Can you see? So this will be R1 and R2, and a new thiol group is formed. Just keep this example in mind. And this reaction can happen within the protein. It can also happen between the proteins. Now I have a protein with the thiol group. I have another protein with a disulfide, right? Now, this reaction is very favorable. Thiol want to react with another disulfide to create an aggregate. This will become an aggregate. This is protein number 1. This will be a protein number 2. It will become an aggregate like this, following this reaction. Am I clear? Right? Now we can see that two proteins are interacting and form a new aggregate, and that can happen with multiple things, and then they can become a big aggregate, right? Now, how heat is helping this reaction? If the thiol group is buried inside, it wants to interact with the disulfide bond, but to interact these two proteins together, the thiol group should be available. It should, otherwise they don't touch each other. When there is no touching, no chemical reaction, right? There should be collision between the molecules. So now, because of heating, you'll slowly open up the protein, and thiol group becomes available. Now this thiol group interacts with the protein, another protein, and you get an aggregate if it happens with too many proteins. Is it clear? And that's how you're making and breaking the bond. You broke this bond and you made a new bond. Can you see here? and heat is helping this reaction. Any question about thiol disulfide exchange reaction? Is it clear? It's one of the common protein modification we do in most of the food science laboratories. Thiol disulfide exchange reaction to create aggregates. Okay? Now, just to show this table here, these guys took, I think, pea proteins here and cow pea proteins. What these guys are trying to see, to what percentage protein denatures with respect to heat treatment. You can see that increasing heat treatment increase the percentage of denaturation. I think the A8 and A10 was pH, if I'm wrong. Yes, this is two different pHs. So now you can clearly shows that by heating, you can partially unfold the protein. When you partially or fully unfold the protein, it will allow for more number of chemical reactions. So heat is one of the methods to modify proteins. Easy, simple, just a water bath or a oven is needed, and it's also very scalable. Some practical examples here. You can clearly see that sometimes solubility is not changed, and sometimes solubility is increased, sometimes solubility is decreased depending upon the heat treatment. It's simply because the type of interactions present among proteins. If it is hydrophobic, usually heat has generally no effect. If it's hydrogen bonding, maybe they becomes more and more soluble. It also depends upon you have whether albumins or globulins, right? So heat can be used to improve the solubility. And here you can see that they tried to heat, soy proteins, exactly. They tried to heat soy proteins, and you can see that at 55 degrees Celsius and 85 degrees Celsius, they heated the soy proteins. This is control, means no heat treatment. The foaming capacity was this much. And when they heated the soy protein, the foaming capacity increased. You remember foaming capacity? Remember that glass jar experiment, the foam formation? Foaming capacity is how far it will go in this direction, right? Foaming stability, and that is also dramatically increased. You can see that the foam was unstable, means it just forms, maybe it came down, but by heating these isolates here, the foaming stability increased up to 30 minutes. They could keep it, I think, in this case, and that is the amount of that's the percentage stability they found, about 80%. Is it clear? So foaming stability can be improved by thermal treatment. Then a little bit about gelation. Heat treatment improves gelations. This is something we fundamentally do in our laboratories. I think many people have done least gelation concentration. That's a common approach we use. Basically, the minimum concentration of protein or treatment where we see gelation, that the thing doesn't fall down when you make it upside down. You can see that with respect to temperature, gelations are changing. So just to give an idea here, you don't have to read all these tables. Just to tell you that heat treatment can be used to gel the proteins. Okay. This is another example for emulsion activity, and they saw increase in some cases, no changes with respect to heat treatment. But the most interesting thing here is that coming back to our anti-nutritional factor. One thing I wanted to highlight here is that when I use the techno-functional property in my lecture, I cover all the functional properties, plus I'll also cover digestibility, flavor, and anti-nutrients. And some people do not include that in the techno-functional property, but in my lecture I include. Is it okay? So here you can see that by heating, basically they reduced trypsin inhibitor in this case activity. It's one of the very, very efficient method to inactivate proteases, heat treatment. That's what most of us do. And that's the reason why food has to be cooked. The reason why legumes has to be cooked before we eat, right? Trypsins makes proteins undigestible, because I taught this yesterday very in detail. I don't teach it again. Trypsin is an enzyme that hydrolyzes protein in your stomach. If there is another protein called trypsin inhibitor that interacts with trypsin and makes trypsin inactive. When the trypsin is inactive, It cannot digest the protein in your intestine, and you have indigestion, what we call, right? So the protein digestibility will be compromised. By heating, you can kill or inactivate trypsin inhibitors. Lot of examples are there. I just found only one here for you. Okay. And I don't take all these other things. People also use ohmic heating and microwave heating instead of just taking the water bath to improve the functional properties. You can do microwave treatment and ohmic heating. I don't show anything about that. Just to let you know that there are other types of heating you can do. Then I'll go a little bit towards the gamma irradiation. It's in this case, the physical treatment, what we are doing is light or high energy radiations, right? Gamma irradiation. Have you heard about gamma irradiation? So I'm sure you know this figure, right? The figure talks about the wave length. It also talks about the energy, right? Light is a form of energy, right? Yes, right. Good. Now, if you look into this figure from left to right, the energy is increasing or decreasing? Left to right. Which one is more energetic radiation? Is microwave radiation is energetic or gamma radiation? Gamma radiation, right? Gamma radiation is highly energetic radiation. Please, I mean, I don't teach you chemistry again. Waves or the light can bring some changes in food, right? For example, radio waves have, people say they do something, but usually they don't do anything because they can't change any chemical thing, right? Then we have a microwave. What does microwave do? They rotate the molecules and you get heat. For example, you can make your coffee hot very quickly in the microwave, right? Then we have infrared. They are the heat radiations, right? What chemical changes they bring? They can vibrate, they can make bending of the bonds and so on. That you have studied in the FTIR last time. Then we have visible light. They absorb light. For example, we are all colored. I am white. No, I'm not that white. I'm sorry. So we are fair and I have black hair and somebody has a white hair. Milk is white or anthocyanins are purple because they absorb light, visible region. Then you have UV light. They kill bacteria, more energetic, right? Then we have X-ray. X-ray has a very high penetration power. So you go and fall on under X-ray machine, they can see your bones, right? Because it passes through the muscle, but may not be through the bone. So then you get the bone cracks and so on. They are very energetic, X-ray. Then gamma radiation comes after X-ray, means it's extremely energetic. It can bring a lot of chemical changes. Am I clear? Gamma radiation is extremely energetic. It can bring lot of chemical changes. It can break the bonds instantaneously. Okay, it is so energetic, it can break the bond, it can knock off the electrons. So that is the gamma radiation. The mechanism of gamma radiations, I don't teach you a lot here, just to show you that when you have radiations, they can do homolytic cleavage of water molecule, then you get hydroxyl radical and hydrogen atom. I think in one of my previous lessons, I mentioned to you is that hydroxyl radical is extremely reactive, very oxidizing in nature. It will oxidize everything. Proteins, lipids, carbohydrates, whatever it polyphenols, it will just oxidize. Okay? It can interact with proteins, can oxidize proteins, and can hydroxylate proteins. Now, the original protein was like this. Okay? Now, if I have a hydroxyl radical formation, and that can add it to the protein ring, and then I get a new protein with OH group added. Now, in chemistry, you know that OH groups are polar, right? So now it gives you another property to the protein. Am I clear? And we also know that OH groups will make hydrogen bonding, right? Originally, this protein was not capable of making hydrogen bonding because it does have only aromatic, for just to give an example. Now, because of this gamma radiation, I created hydroxyl radical, and hydroxyl radical can attack proteins and can hydroxylate protein. Hydroxylation changes the polarity of the protein, can increase the hydrogen bonding tendency. Now the protein-protein interaction can be changed. When the protein-protein interaction changes, functional property will be changed, the digestibility will be changed, so many things will be changed. Is it clear? I just give one example. They can also do a lot of other things. They can make protein carbonyl formation, for example. Many things these radiations can form. They change the primary structure of protein. Please note down that gamma radiations will change the primary structure of the protein. You can see just example here. Originally, there was a phenylalanine here, right? It was phenylalanine. Now I made a tyrosine out of phenylalanine, right? So basically, you are changing the primary structure of the protein. By changing the primary structure of the protein, you change the secondary structure, because secondary structure is dependent on the primary structure. Tertiary structure is also dependent on the primary structure. So the protein folding and unfolding behavior changes. Hydrogen bonding changes, hydrophobic interaction changes, the techno-functionality, digestibility will be affected when you do irradiation or gamma treatment. Physical treatments are physical treatments, but they bring chemical changes. This classification, what I used based on which method you are using to modify, to initiate the product. Okay, is that clear now? But as I have clarified it already, actually, when I say physical modification, it means we use physical treatment to modify proteins and they can bring chemical changes. Is it clear? When I say chemical modification, we will use chemicals to modify protein and they will bring chemical changes. When I say biological modification, we'll use enzymes and bacteria to modify proteins and they bring chemical changes again. Chemical changes will happen, otherwise protein will not change. Right? Chemical changes is important. Just to give one example, just to show here, I mentioned about they change the protein structure. Remember my lecture number 3, we talked about UV fluorescence spectroscopy to see the modification of the protein tertiary structure. Yes, I think they are trying to do this one. They are doing the tryptophan fluorescence, if I'm not wrong. Yes, you can see that this was control, no irradiation, and this one is irradiation. They use different intensity of gamma irradiation. I think GY is called gray, right? They measure it based on gray, right? Gray. Yeah. The for example, how to say, it's a unit of irradiation. It's gray for gamma irradiation. Okay. So you can clearly see that we are having a red shift, right? The protein having its red shift. What do you mean by red shift? Was it hydrophilic, becoming hydrophilic or hydrophobic? I forgot now. You have to go back and see my slide back, right? When you see red shift increasing the wavelength after treatment, that indicates proteins are exposed or proteins are not exposed. The hydrophobic region is exposed or hydrophobic regions are buried. Red shift means unfolding. So you can clearly see that the protein is unfolded. Can you see? Now it's a red shift going toward the higher wavelength. The protein is unfolded. Exactly the same mechanism which I mentioned to you here. You're changing the primary structure, protein unfolding takes place, and you have a new protein basically here. And here is a nice example. They show how you can change the techno-functional properties. One of the good things we can observe, don't read all the diagram, all the words, all the values here, it's not interesting. Just look into the conditions here. They're increasing the dosage here, right? They're increasing the irradiation dose, and you can clearly see that the oil binding capacity is increasing. Okay, emulsion activity is increasing, oil in water. Emulsion stability is increasing. Okay, water holding capacity is somewhat decreasing. This is decreasing, right? Now, can you correlate this one with this one? What is exactly happening? What kind of protein structural changes changing? And here they can see that it's from another paper. They show how emulsification capacity, how emulsion stability and protein solubilities are changing with respect to gamma treatment. In this case, increasing the radiation dosage increase the solubility of the protein. Again, probably because you are getting more and more hydroxyl group, or you're making more and more carbonyl groups because of the protein oxidation, and they will change the solubility of the protein, and that you will see here, right? When the protein solubility changes, all our emulsion behavior and everything will change. Okay, in this case, at least they saw increasing foaming stability with respect to increasing radiation dosage. Again, I'm repeating, don't worry about this all bar graphs. Just remember the take home message. Take home message is gamma radiations will change the protein primary structure, right? They will make proteins perhaps more polar, or they expose more hydrophobic region, and that will change the techno-functional properties. Another very interesting thing I found is that in that paper, they also showed that you can increase the protein digestibility by gamma treatment. There's a lot of reasons why the digestibility increases. One of the fundamental reasons could be protein unfolding. Unfolded proteins are apparently more digestible than the folded proteins, because usually that is, plant proteins are less digestible simply because there is a high degree of folding, right? And now you unfold them, maybe they're more accessible to enzymes in the stomach. In this case, the in vitro protein digestibility, though it is more accessible to enzyme, and you will get a better digestion. And also, because of because of gamma irradiation, protein can also be cleaved. Okay, peptide bond can also be cleaved because of gamma irradiation, and then apparently the digestion will immediately increase. Okay, it's another example here how the gamma radiation is improving reducing the allergenicity. You can clearly see that the percentage inhibition when you use the gamma irradiation. That's fantastic, right? It's one of the biggest challenges, allergenicity. You can use gamma irradiation to remove the allergenicity. Now, I'll ask a question. I told a lot of good thing about gamma irradiation, right? How it can do many things. It can improve digestibility, it can improve emulsification, foaming, blah, blah, blah. What could be the disadvantage?
No regulatory standards.
There is no regulatory standards. Yes, you are a very good point you raised. However, in Americas, in the USA, gamma irradiation is allowed, but not for the protein modification. I don't know, but they use gamma irradiation to kill the bacteria on the surface of some food products. In the EU, it's kind of regulated. In the US, they use it a lot. For example, they use I'm on camera, but I think they also use it for meat, if I was not wrong, to kill the surface bacteria. I'm not very sure how to read my article, but I remember like that. Okay, I might be wrong. But that is kind of approved in the US, but I don't remember it is approved for the protein modification per se, because the rules changes. They also specify which food products can be allowed to modify with radiation. When I say radiations are allowed, it does not mean that they can use it for every single kind of food. No, that's not the regulation. Regulations are usually specific to certain food commodities. Okay. Another disadvantage, yeah.
When we talk about in terms of safety, we are inducing any raise in the food product
Yes.
to cause some changes, to improve its techno functionality. But there is a con side of this, that there may be possible, means after doing the safety evaluation only we can come to a conclusion that these rays may result in the formation of some toxic components whose effect on human health can be negative.
Absolutely.
There is possibility of formation of toxic
Unwanted components
Yes.
or potentially toxic molecules that can generate. In fact, I am doing research on this particular topic. That is my core area of research at the University of Copenhagen. I'm trying to investigate how this physical and chemical treatment, because all my colleagues or other part of the world, they're all focused on, oh, digestibility, oh, techno-functional property, oh, I have to improve this one, oh, I have to decrease this one. Okay, what about the chemistry you're doing? You're changing a lot of chemistry here, right? But we are focusing like this, right? Oh, I just want to improve the solubilities. I don't care what else will happen. But many things are happening because chemistry is a very crazy thing. It is not selective to one amino acids usually. They will start damaging so many things. The protein is so complex, right? And I'm trying to investigate what kind of harmful compounds are formed during these irradiations and so on. And I'm trying to feed to animals and see if the animal dies or it becomes super happy or it becomes super crazy. So those are the investigate. I'm not telling they're bad, huh? Please note that we don't know. Yet there is less toxicological evaluation on the protein modification. There's one thing I have to keep it in mind, because when I say the treatment of whole food, it's a different story. Because then they treat on the surface. Let's say you take broccoli as an example. You want to kill the bacteria on the surface of broccoli, right? It's a vegetable, right? You're just doing a treatment on the surface. Now, if I want to treat this is a broccoli, okay, then I will apply the gamma radiation here, right? Now, in our case, what we have to do to modify the functional property, we need to take it in solution. Do you agree? Now, the protein is dissolved in solution. The chemistry, what happens here, is very different than the chemistry what will happen here, because now more and more molecules are interacting with the gamma radiation, because gamma can penetrate through solution. It can attack almost all protein molecules now if you put a good intensity or good gray here. So the story are different here. So if the gamma can be used on chicken fillets or broccoli, gamma may not be useful on your protein ingredients, because the way that is being treated is different. When the way you treat is different, the chemistry is different, toxicology will be different. We are still continuing with the lecture number 12, chemical and enzymatic modification of proteins. We have discussed about physical modification technique, especially radiation, gamma radiation, how it can be used. And now we will move on to the other technique called UV radiation. Before I start my other part of the lectures here, I must have to mention that I've been discussing with some of the friends here. This lecture requires little bit chemistry background. This lecture requires little bit chemistry background. Because I'm going to talk a little bit about chemical modification and so on. And I also know that some of you might not be having that much chemistry that in your bachelor's, studied in your bachelor's or master's. So you might find this a little bit overwhelming, but don't worry. The important thing for you here, those who are sitting here, is that at least look for the take-home messages. At least think about what are the different technologies are present. Since this lecture is being recorded and I cannot make it too simplified, because maybe some other people it may be useful. In the future, you might have to find it very useful. Then you come back and go to YouTube and see my lecture. Oh, sonication. Oh, this is what happening, right? And that's the reason why I will not too dilute my lecture, but I will not make it too complicated either. I'll try to teach you the basics, okay? If you don't understand, do not hesitate to raise your question and ask me to explain again, okay? So UV radiation is something similar to gamma radiation. In case of gamma radiation, we use the very high intensity, very high energetic radiation. In the case of UV, it's energetic but less energetic than the gamma radiation. Basically, we use a UV light, and UV light has a wavelength between, let's say, 200 to 400 nanometer, and at this particular wavelength, the light, the photons are sufficiently energetic, they can excite the electrons, right? UV light is sufficiently energetic, they can excite the electrons from one orbital to another orbital. This is something we have studied in our previous class when I was talking about fluorescence spectroscopy. You remember this diagram? Right? The electrons were here and it went here by absorbing light. You remember my Jablonski's diagram, it's called, right? So basically, UV light can bring chemical changes by exciting electron from one orbital to another orbital. I will not teach it so detailed considering your background, but I'll give you brief information how exactly UV can bring changes, okay? Very briefly. So, these are the three different energy levels, let's consider, okay? Different energy levels. Now, I have two electrons here. This electrons belongs to protein where the amino acids having aromatic structure. What are those? What are those? Phenylalanine, tyrosine, and tryptophan. Phenylalanine, tyrosine, and tryptophan, these are the three amino acid residues on protein. They are UV active. They are photosensitizer. That means they absorb UV light and can go to higher energy state. Okay, that is their inherent molecular property because of the aromatic rings. Am I clear? Just remember that on a protein, There are 3 amino acids, tryptophan, tyrosine, and phenylalanine. They are UV active. That means they can absorb UV light. When they absorb UV light, they can go to higher energy state. Now, imagine these are the 2 electrons of tryptophan. Just imagine it absorbs light. Which light? UV light. Let's say it's absorbing at 280 nanometers specifically. Now, there were 2 electrons like this. These were the 2 electrons. Electrons are oppositely spin now. Now you apply UV light. What happens? Tell me. First step. Electrons will absorb the light. Light is a form of energy. So it will go to higher energy state. How long it will go? It depends upon how much the energy it has absorbed. How long means how many orbitals it can cross, right? So imagine it absorbs UV light and it went to higher energy state here. It's called excited states. Okay. And here the electron spin is the spin. Spin means now these are oppositely, the spin of electrons are opposite in an orbital, that Pauli's exclusion principle and all these things I don't teach. So it will go to higher energy state without changing the spin. Spin is the same, means it is rotating now parallel or anti-parallel, it will not change. Okay. You are at home, imagine, in the evening, and you are tired, and you got some energy, and you want to went to terrace, right? You will enjoy in terrace for a couple of minutes, couple of hours. But will you sleep at the terrace? No. You will come back to home, right? Like that, electrons also will do. When they take some energy, they go to higher energy state and they will come back to home. But while coming back to home, if I were like, there are a lot of steps, right? From terrace, there is a lot of steps. There's a lot of possibility how you can come back. This is you are inside, you went to the terrace, right? And while coming back from home, back to the home, to your room, you can do it in multiple ways. One, from the terrace, you jump directly, right? From the terrace, directly jump directly. That's one of the possibilities. Second possibility, from the terrace, you jump to the sub-terrace, because usually there will be 2 terraces in homes, right? From the first terrace, you jump to second terrace and then jump back to the ground floor. Second possibility. Third possibility, from the terrace, jump back to the second terrace, then take the stairs. Third possibility, right? So electrons can also do in a different ways, they can come back to the ground state. One of the possibilities, they take the energy and suddenly can jump back the state, but energy levels are divided into vibrational energy level. So basically they come back to the another energy level by releasing the heat radiation. I have taught you before already, right? And then they can come back to the ground state. And what is this? By emitting the light back. What is this phenomenon called? Fluorescence. That I have taught. The fluorescence spectroscopy works exclusively on this phenomenon. Did any chemical reaction happen here? No chemical reactions has happened. Remember, it's only physical phenomenon. Light has been absorbed, heat has been reloaded, remaining light has been released. It's just a physical phenomenon. But some cases, chemical phenomenon can happen. What will happen? The electrons took the energy. Okay, you got a cup of coffee. Okay, now you got energy. You went to the terrace. In reality, you should have come back to the ground state, that is to your home. What you will do, you got a crazy idea on the terrace. Okay, you will stay in the terrace for a few more minutes there. Okay, you get a lot of crazy ideas. You can bring another friend together with you. You can fight with him or her, right? A lot of things can happen on the terrace now. And the electrons also like that, crazy. They really wanted to come back to the ground state. They don't want to come back. I'll stay in the terrace for a while. What they will do, they can ionize. That means they can disappear now. The electrons, instead of coming back to the ground state, they can ionize. The molecules, the tryptophan can ionize. Now the tryptophan was originally like this one, with a good number 1 electron. It releases an electron. Okay, that's called ionization. We call it as photoionization because of the light, right? Now, tryptophan is surrounded by oxygen. For example, you take a protein in solution, There's always water and oxygen. There will be dissolved oxygen every time in food, right? Electrons loves oxygen, or oxygen loves electron, and oxygen becomes a new molecule called superoxide radical anion. Superoxide, have you heard about it? Superoxide radical anion is an oxidizing agent. It can oxidize some other molecule, right? You went to the terrace like this one. You should have come back. You did not come back. While coming back, you will not jump to your own terrace. You will jump to other home's terrace. You're becoming monkey now, right? So electrons are also having an overlapping orbitals or shells here. They should have come back to the ground state, right? Instead of coming to the ground state, they jump to the other orbital by changing their spin. That's like you went to the terrace, you should have come back. Instead of coming back to your home, you jump reverse like a monkey, changing your spin, and then you will come back to the ground state, and that is called phosphorescence. You know, heard about phosphorescence? And this will take a little bit time. Why? Because you have to went up, instead of coming back to your home, you went to others' home terrace, and then you came back to your home. And that takes time. Usually fluorescence is delayed. Radium watch, you get the light in the night. That's fluorescence. Now, that is the second phenomenon is happening. But sometime what happens, while jumping back from the electron, they actually interact with other molecule. Somebody else is on the terrace, they react with them, and they can generate another superoxide radical, and sometimes they transfer their energy to other oxygen molecule, become singlet oxygen. I don't teach this all this thing in detail, it's not required for my today, but just to let you know that because of this light transition, you get reactive oxygen species. Can you see? These oxygens are highly reactive, they can oxidize proteins. All right, now just to show you that you can clearly see that how the light treatment will change the gluten structure here. You can see this is where the proteins are supposed to absorb. There's a change in this. Those secondary structure can be changed. And here they show that UV treatment actually increases the thiol group in gluten. It's simply because when you have a disulfide bonds on a protein, because of the UV light, through different mechanism, I don't teach all this mechanism, you can get more thiol groups. Clear? So disulfide bond can become thiol group because of UV treatment. Exactly the same mechanism I showed you. It forms reactive oxygen species. Sometimes disulfide bond can directly absorb the light. They can be cleaved. So it becomes more and more thiol group. Okay. So increased thiol group means maybe increased thiol disulfide exchange reaction. You can get more aggregation or less aggregation. Is it clear? Another nice interesting paper I found that they found that gliadin is an allergenic protein. By UV treatment, the allergenicity can be reduced. By UV treatment, allergenicity can be reduced. If you really want to learn more about irradiation, light, UV, gamma, how it affects techno-functional properties, try to read this nice paper. Okay? When you're free, just read this review article. There's a lot of information about it. Now we will move on to sonication. I think I taught this on the day 2, ultrasound assisted extraction, right? Remember the mechanism? Ultrasound is nothing but we will use high intensity, low frequency ultrasound radiations. And these high intensity, low frequency ultrasound radiation, when they're propagating inside a solution, they create a small vapor filled bubble because of the movement of the wave, contraction and rarefaction, compression and rarefaction. Basically negative and positive pressure between the solvent molecule, then you get a small micro bubble. The bubble will increase the size as soon, continuously applying the sonication power here. At some point, they implode. When they implode, they release energy in the form of heat up to 5000 degrees Celsius. Pressure will be very high, and at very high temperature, it's happening not completely in a small portions inside the solution, it creates a microjets, and that microjets can explode the cells. Okay, and that can change the extraction behavior. That's what we have studied. But that can also do some chemical changes. Because some people say during sonication, you can have homolytic cleavage of water molecule. It will give you hydroxyl radical plus same as before. I don't believe this because there are some proof. I have to believe it. There are some proofs, but it might be not as efficient as gamma radiation, just to let you know. It's not as efficient as gamma radiation. It can produce. And I have already discussed about how hydroxyl radical can damage proteins, and the damage have a different functional properties. Is it clear? And some people also say that it will change the hydrogen bonding and other things simply because sonication is always associated with heat. Right? When you know your water bath, you turn it on for half an hour, it becomes hot. Right? Sonication is associated with heat, and heat will change the protein structure, which we have already shown in my first part of the lectures. Is it clear? So please note that sonication is very unlikely to bring a direct chemical changes. It's not that efficient to bring the chemical changes, but it will indirectly modify the protein. Indirectly by releasing the heat or by releasing the hydroxyl radical. Am I clear? Sonication will not bring direct chemical changes because it's a very weak waves, very less energetic waves. So molecules do not have a chemical changes because of ultrasound. It's just a sound waves. Am I clear? So there are some studies, they clearly show that you can change the secondary structure of proteins by sonication, and they can show that you get the increased water holding capacity by sonicating the proteins. You can decrease the turbidity by sonication. You can change the water holding capacity. This is emulsification. You can change the water holding capacity. It's simply because when you do the sonication, because of the thermal effect or because of the oxidation effect, protein will denature, more exposure, more interaction. That's it. Right? And why turbidity changes? Reduction in the particle size. So you can use ultrasonication to do these things. This is a nice paper I saw. They found that ultrasonication inactivates trypsin inhibitor, which is super cool because trypsin inhibitor is an inhibitor of the digestion. So that can be solved, that problem can be solved using ultrasound treatment. Okay, and they're showing that increasing I think, I'm not sure whether this is a treatment time or something like that, that decreases the trypsin inhibitor activity. The same paper, they also showed us that ultrasound treatment increases the protein digestibility. Again, something related to exposure of the amino acid, denaturation of the protein, right? It's not so efficient. You can see that they were at around, how much is this? Maybe 75, and they reached 80. It's a poor way of representing scientific data, according to me. We are just trying to hype it, right? It's only a minor change, but we cut down the axis. Can you see? You're not allowed to show axis like this in scientific diagrams. You should show from 0 to 100 here, right? They're trying to show the comparison here, and that's the reason they want to show it. For me, it looks like, oh, there's a lot of change, but in reality, it's only a minor change. Am I clear? So whenever you make a scientific diagram, don't oversell your data. Tell the facts, right? You don't have to tell that ultrasound increased digestibility significantly. Yes, there is a significant increase. From D, it becomes A, right? Statistics show significant. But in reality, it's maybe a minor change. Am I clear? So don't take home message is not that ultrasound will dramatically change the protein digestibility. No, I don't believe. Small change might happen. Another beauty of scientists is, I must have to mention here, we will only publish when we get a good result. Do you agree? We will only publish when we get a good result. We dare to not to show the negative result. That's the problem of the scientists, especially the PhDs, and including me when I was a PhD student. If there is no digestibility change, I would not put that data on my paper. People think the reviewer will be unhappy. Oh, no change in the digestibility. Why the hell I am doing this sonication experiment? It's a bad. Yeah, exactly. It's a bad idea of doing that one. As a scientist, you should always show good and bad. Because now I'm teaching these lessons, I'm trying to find some articles. Everybody's showing only positive thing. Nobody's trying to show the negative thing. Out of 100 cases, maybe 80% cases, digestibility did not change. Maybe it's even reduced after sonication, right? So when you do not only sonication, I'm telling about all the treatment we are doing. So try to show both positive and negative result. Don't believe in only positive result. My lecture is going in a way that I'm only showing, oh, trypsin inhibitor activity increased, oh, digestion is increased, oh, foaming capacity increased. Maybe 10 out of 100, this is the case. Out of 80, nothing is changed, maybe it's changed negatively. That's also another take-home message. Am I clear? It's not necessary that the treatment will always improve the functional property. It might not do anything. That is the case of PhD student. I have a lot of people working like that. They come and say into my, Mahesh, I tried so many things, nothing is working. Okay, now increase the temperature. Oh, now increase this one. Still nothing is changing. It's a common thing. Don't worry, okay? Some extrusion, I have already taught what is extrusion. Extrusion is to get the meat analogs, the texture structure. Remember, here in this region, the temperature can go up to 180 degrees Celsius, and then you will cool it here. So heating and cooling, that can check the protein structure. Protein can be denatured. I have explained all these things already in the previous lecture during extraction. Protein denaturation, protein cross-linking happens, and that will change the protein three-dimensional structure, and that will change the functionality. So you will start getting different structures. I'll not explain this again because I've already taught you previously. Then there is other technology called cold plasma treatment that can be used to modify proteins. At the interest of time, I will skip that for today, but I'm not skipping it from the GAN course. I will teach it in another lecture because it's also relevant in the another lecture. Cold plasma is nothing but it is the plasma, fourth fundamental state of matter. It containing electrons, UV light, everything. Sun is in the plasma state, you know, right? But it's hot plasma. We can generate plasma in cold condition. It's not cold in reality. It's room atmospheric condition. So then it's called cold plasma. It contains reactive oxygen species, reactive nitrogen species, and they will attack the protein. They can modify the proteins. Okay. And that will change the functional properties of proteins. And new technology. We are also working in my laboratory about cold plasma, how we can use the technology to modify the protein. Now we will move on to the chemical modification. So we talked about the physical modification. We talked about heating, gamma radiation, UV light radiation, sonication, and briefly about cold plasma treatment. But cold plasma will cover later. Now we will go to the chemical modification. Okay. When I say chemical modification, it's not the modification of proteins. Proteins are chemically modified. It's basically usage of chemical reagents to modify proteins, right? When you use the chemical reagents to modify proteins, then we call it as chemical modification in this context, and that will change the chemistry of proteins. In other words, okay. The first one is glycation, also known as the Maillard reaction. How many of you heard about Maillard reaction? This is something people will always teach if you take food science and technology, right? Any course in food science and technology, they should teach you Maillard reaction. Because Maillard reaction is one of the common reactions happens in food system. It's extremely common. I have some examples. The bread, right? Usually we don't eat bread directly. I mean, kids usually use it. You open the packet, you just eat it. But some people like to eat the crust of the bread. It has a different aroma. Do you know that? It has a different texture. It has a very different taste. Go to pizza, for example. Pizza, the central portion has a different taste and texture compared to the side one. It's a Maillard reaction happening there. That gives you that taste, right? When you put it in the toaster, it gets a different taste, right? And now let's take potatoes. This potato I really don't want to eat. But if you give me French fries, that tastes better. Taste is really good, French fries, right? Now I have a chicken, no coffee, the green coffee, not good. Black coffee, nice aroma. Now let's take my favorite chicken. If you boil it, it has one taste. Now if you make a tandoori chicken, It has a different taste. Do you agree? And the tandoori chicken has that crispiness, that redness, mouth watering. But we need to eat plant based, okay? We need to eat plant based. This is only for the diagram, but eat tandoori chicken, it's healthy, no worry. Okay? But what I wanted to say that there is a lot of chemical reaction happening during cooking and roasting that changes the color, flavor, taste, texture, everything, and that is called the Maillard reaction. It's called as the Maillard reaction because Maillard was the French scientist who discovered it back in the days. Okay. Okay, now I'll show you a little bit about the chemistry, what is exactly happening in the Maillard reaction, right? Almost every food contains proteins, not all, almost, right? Almost every food contains sugar, carbohydrates. There are some sugars called reducing sugar, it contains reducing ends. When they come together, okay, protein has an amino group and sugar has this reducing end over here, okay? You're heating them. For example, chana pora, it has milk proteins, it has what they are sugar, sugar, they are sugar. Sugar is glucose and galactose and all is sucrose, basically sugar, right? And then they're heating it continuously, and then they start reacting together and they form Maillard reaction. And the consequence of Maillard reaction is that you get that chana pora crust, that one, and then you get that nice flavor of chana pora chicken, whatever. It's all because of Maillard. It's a very complicated reaction, one of the most well investigated. Please remember that the reaction happens between sugar and protein or amino acids or peptides, basically amino groups. It looks very simple. Trust me, during Maillard reaction, they say 1,000 different kinds of molecules are formed. I'm talking about 1,000, maybe more than 1,000, just because of these two reaction. Very complicated, produces numerous reaction, and that changes flavor, texture, color of the food. I mean, I know a little bit chemistry knowledge is required, but I'll quickly go through the mechanism, not in detail. So you have a glucose, for example, sugar. Sugar contains a reducing end, and you have an amino group, for example, protein, which contains an amino group, right? Carbonyl groups are electrophilic, amino groups are nucleophilic, and they have a condensation reaction, and then you get a Schiff base. That's the first product of Maillard reaction, and the Schiff base will rearrange and forms Amadori compound. This is the first stable product of the Maillard reaction. I will teach Maillard reaction for 4 hours back in my university, but I have to teach in 4 minutes now. It's a very complicated, but I'll just tell you what exactly is happening. So it forms Maillard reaction. First is Schiff base, and then it forms Amadori compound. But the reaction will not stop here. Basically, what exactly happened here is that you have a protein contained amino group, and you had a sugar. This was a sugar with the reducing end, right? And they react, and now you get a protein connected to a sugar. It's called glycation. Glyco means sugar. Protein glycation means a sugar moiety is attached covalently to a protein. Now, originally it was a normal protein. Now you got a protein attached to a sugar. Now it's a different protein. Do you agree? Now we are doing the chemical modification of protein. That is called Maillard reaction. Okay? But the reaction does not stop here. They further undergo lot of complicated mechanism. They produce volatile compound, they produce highly reactive compounds, and that will change the flavor of the food. For example, this reaction go further and forms a very reactive compound called alpha dicarbonyl compound, C double bond OC, dicarbonyl compound, 2 carbonyl groups, right? For example, one of the famous one is, let's say, glyoxal. Is extremely reactive, and this reacts with another amino compound. For example, amino acid undergoes Strecker degradation, forms volatile compound. Volatile compound. That's the reason why bread smells so good. That's the reason why tandoori chicken smells so good, because of the Strecker degradation. It forms volatile compound, right? In some cases, this dicarbonyl reacts with protein and forms advanced glycation end product, we call that AGEs. I'll show that later. And if advanced glycation end products, probably not good for your health. Acrylamide can also form in the same pathway, and she was talking about acrylamide. People say that don't eat French fries a lot because it can have acrylamide. Acrylamide is a well-known carcinogen. So some of the chemical reactions are good, flavors are really good. Some of the chemical reactions are not good. It can compromise the digestibility, can form unwanted compounds. It might have a health effect. That's the beauty of Maillard reaction. It's really good, traditionally used. I'm not blaming Maillard reaction, a fantastic reaction to happen. Without Maillard reaction, 90% of food tastes not good according to me. We like roasted cooked food because of the Maillard reaction, okay? So you read this paper, okay? You take a photograph of this one, you read this paper. We have it's actually one of my colleagues, and she has summarized how different methods can be used to reduce unwanted compounds in Maillard reaction pathway. A lot of technologies. As I said, it's my 4 hours lecture, I can't teach now, okay? And Maillard reaction also forms very colored product because it forms melanoidins, and the melanoidins are the responsible for that the crust, and the crust becomes brown. They are all becomes melanoidins, okay? Very complicated structures. Okay, now let's forget about Maillard chemistry part. Think about they change the structure. Can you see? Maillard reaction, because of the protein sugar interaction, glycation, structure will be changed. When the structure changes, functionality changes. Please note that sugar is usually polar. Now you're adding more and more sugar to the proteins. What happens? Solubility will be changed. So that is another reason why we are doing the glycation. When the solubility changes, water holding capacity changes, oil holding capacity changes, emulsification changes. So it's all interlinked with the solubility. So Maillard can change the functional properties. Sugar can also create hydrogen bonding. So the protein folding will change. So that will change the functional properties. So here is one example. They show how pea protein concentrated heated with glucose, how it changes the solubility. I don't want you to remember the graphs again and again. Just remember that something will change. Okay. And it's a nice summary. They show that they change the bioactivity, it changes the solubility, it changes the emulsification ability when you do the glycation. There's a lot of studies. It's not something new. Okay. And coming back to your own question that you asked, the Maillard gives you dicarbonyl, and dicarbonyl gives you some other intermediates, and the intermediates gives you the aroma compound. It's very nice in some cases. Now, I want to prepare a protein drink, okay, for infant formula, imagine. I want to prepare a protein drink for an infant formula. I'm glycating the protein to improve the solubility, right? Now, that infant formula is smelling like a chicken broth. Is it good one? No. Right? Please note that Maillard reaction is good, but you have to control it. Otherwise, you will get sometime aroma is good, sometime aroma is not good. It depends upon which product. Chicken should smell chickeny. Milk should not smell chickeny. Am I clear? So you have to be careful when you do Maillard reaction because it can create some flavor. Flavor is not always good. Sometimes it's bad. However, you can use Maillard reaction to get meat analogs to have a meaty flavor. That's good, right? Because we want to get the meaty flavor in meat analog. Maybe you can use Maillard reaction there. But infant formula, no, I don't want to use it. So depending on the application, it's good and bad. Now, Maillard reaction can also cause sometimes gelation, unwanted aggregation. Keep it in mind. Sometimes it's good, sometimes it's bad. Maillard reaction can also release this advanced glycation end products I was talking about, and that might have health consequences. There are a lot of research on this. They show that some of the Maillard reaction might be bad. However, it's not completely confirmed. The research in this particular area is like blah, 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 because they have done a lot of mice studies, but they feed this much amount of advanced glycation end product to mice, and mice will, of course, get crazy. But if you continuously eat roasted food, especially if you do fish fries, if you continuously like only the roasted part, it is bad. Because there's a lot amount of glycation in product. They might be bad, but there is no full complete health studies on this one. I have to emphasize this one. There is no health studies to confirm it's really bad. This is the example here that show how much unwanted compounds forms. CML is an advanced glycation end product. You can see that by doing this glycation, you produce a good amount of unwanted compounds that might have a health consequence. One of the biggest challenge here, due to the glycation, we lose the lysine. Lysine is an essential amino acid. During glycation, you basically react mainly with lysine residues. Lysine reacts with sugar. So most of the plant proteins have less amount of lysine, and now you are modifying them. It's not good. Am I clear? Now we'll move on to phosphorylation. Phosphorylation is a technique we can use to modify proteins. As the word says, it's nothing but adding phosphate groups to the protein. Okay, basically you have a protein, right? And the protein contains, let's say, serine residues, and serine residues contains hydroxyl groups. Okay, and if you interact with the phosphate containing molecules, when you interact with phosphate containing molecule, the phosphate can interact with hydroxyl group and you get a phosphorylated protein, something like this one. Can you see the structure? Now, if you look carefully into this mechanism, what did we convert? What happened actually? You had a protein, right, with a hydroxyl group, right? I converted this into a group containing phosphate. What exactly happened? So there was no charge here from the hydroxyl group. Now I'm getting more and more negative charge. Basically, you're converting protein into negatively charged component. Again, coming back to my very first class, solubility. No, the fourth lecture, solubility. Solubility is dependent on the charge, right? Now, you're changing the charge of the molecule. That means you're changing the solubility of the molecule, and charge is also related to the pi, right? When equal number of positive and combines with equal number of negative, net charge becomes 0 and protein precipitates. Now you're changing the charge of the protein. That means you're also changing the pi of the protein. Am I clear? Remember, plant proteins are always having the pi 4 to 5. Now you're changing the pi of the protein to another level, and that will change the solubility and that will change the functionality. Is it clear? Basically, we're changing the surface charge of the protein by doing phosphorylation, and the surface charge will change the solubility, functional properties. Now protein is getting more and more negative charge. It can also interact with other molecules indifferently compared to previously when it did not have that much negative charge. So that will change the functionality. For doing phosphorylation, they use a chemical called sodium trimetaphosphate. It's called as GRAS. I hope I have a point. Yes, GRAS means not the grass. It generally recognized as SURF by FDA. So you can use it in food in a certain extent. Okay. Instead of that, you can also use phosphorus oxychloride or phosphoric acid to modify the protein. But please note that you're not only modifying serine residues, lysine can also react exactly in the same pathway. Lysine is an essential amino acid, so modification can compromise the nutritional value. Here is an example. They show that increasing the content of that what is that called, STMP, the phosphorylating chemical, the rate of phosphorylation is increased. At some point it decreases because you add more and more phosphate compounding group, you change the reaction condition, and that will compromise the phosphorylation. So basically you can optimize the extent of phosphorylation by controlling the amount of this chemical you use, right? Please note that modification is not something like you need to completely modify protein. You can control it to get the desired charge. And here is an example that shows that you can detect the phosphorylation using FTIR, because when phosphorylation happens, there is a specific IR absorption takes place. So you can evaluate easily with FTIR. Okay. And this is the paper that clearly shows that phosphorylation is showing negative zeta potential. It means that you get more negative charge on the surface, right? And this also shows that particle size is changing because of the phosphorylation. Protein secondary structure changes because of phosphorylation. It's over here. And this one I have not covered, so ignore it for now. It's XRD, okay? So take-home message is that phosphorylation changes protein structure and surface charge. Change in the surface charge and the structure changes the functional properties. I hope of some example. Yeah, example is here. You can see that solubility has been changed with respect to this one. Foaming capacity has been changed after phosphorylation. Apparently, the digestibility from 93 it becomes 95. Significant change, but only a minor change in the digestibility. So, phosphorylation can be used to change the techno-functional properties of proteins. You can read this paper if you want to really interested in emulsification and so on. Now we will move on to the another technology to change the techno-functional properties called acylation, very similar to phosphorylation. Instead of adding phosphate containing compound, we will add acetylating compound here, right? One of the common chemicals we use is acetic anhydride. This is here, okay? You incubate protein with acetic anhydride and that will react with amino groups of the protein and you get a new protein with an a group here. Can you see? It's called acetylation. So this new group, can you see it is having a negative charge, right? Originally the amino group was positively charged. You know that the amino groups gets positive charge, right? Now added anhydride. It could be acetic anhydride, it could be succinic anhydride. Then you get a group with negative charge. Can you see? Now we convert a positively charged protein into negatively charged protein as a complete modification of protein, and that will change the surface properties, that will change the structure, that will modify the protein. So you can use two chemicals, acetic anhydride and succinic anhydride. If you use succinic anhydride, we call it as succinylation. Okay? If you use succinic anhydride, we call it as succinylation. If you use acetic anhydride, we call it as acetylation. I have done acetylation. Acetic anhydride is really smells nasty. Don't smell it. It really smells nasty. Okay? It's a good method, but I'm not super happy. You need to remove you need to remove all the unreacted compounds, and that's not easy. This looks really nice, but it's not a good method to do, in my personal opinion. So it reacts with lysine. Please note that it can also react with all the hydroxyl compound containing amino acids. For example, it can react with serine, it can react with threonine, it can react with tyrosine because all of them contains OH group. Okay, so you're not selectively modifying lysine, you're also modifying other amino acids if you do acylation. Am I clear? So basically, a positive becomes negative if it reacts with the amino group. I hope I have some examples here. This is not required. When you're free, just go through it. How do we do acetylation? Just to showcase again, acetylation will change the protein structure. The secondary structure is dramatically modified when you do acetylation or acylation or succinylation. It's simply because you're adding a big moiety here. A big moiety is around 100 Dalton here. If you do a succinylation, a big moiety is added to the protein and that will completely change secondary structure of the protein. When the secondary structure of the protein changes, functionality changes. And this is again, they show how the tertiary structure changes when you do succinylation. You don't have to remember the graph, as I said. Just remember that things change when you chemically modify proteins, and that can be evaluated by FTIR or fluorescence spectroscopy. I have already taught that you in the previous lecture. And here is a good example that shows that zeta potential, how it is changing. You're getting more and more negative charge on the surface, right? And that indicates that, okay, you are changing the protein solubility, you're changing the pi of the protein, you're also changing the particle size, because depending on the charge, they interact with each other, or they attract or they repel, and that will change the functional properties. I don't want to teach so much about acetylation, just to let you know that there's a big table in this particular paper. If you read it, they show all the plant proteins, how they have been succinylated or acetylated to change the functional properties. You are welcome to read this paper. So the take-home message is that succinylation can be used to modify proteins to change the surface properties. But one of the important things you have to keep it in mind when you do the chemical modification, you compromise the essential amino acid content. For example, when you do phosphorylation or succinylation, they react with lysine residues. And lysine is an essential amino acid which is already present in a small quantity in plant-based foods. And now you're chemically modifying them, you compromise their content. You can see that up to 50% of lysine is lost. And there is a serious loss. Already present in low quantity, and you are modifying on top of them. Basically, you compromise the nutritional quality. Of course, you might get the best solubility in the world. You have to keep it in mind that the essential amino acid is compromising. And why I want to emphasizing this one, because when you read the research article, they only highlight the positive thing, right? But you have to, as a scientist, should think, am I damaging the protein in a negative way? Yes. Then you find out. It's very important to know in plant-based world is that everybody is focusing on the functionality. Oh, I want to get the texture, taste, flavor. There's a less focus on the other unwanted, right? So you, as a scientist, you should think, okay, when I modify, am I damaging the protein in a negative direction? And that has to be kept in mind. I like this very old paper. I was talking about everybody published the result when you see only the positive result. And this was a paper from 1986, even before I was born, right? And they were trying to modify proteins, especially the rapeseed protein, by succinylation. And they clearly show that turbidity is compromised. It's not actually creating a good gelation properties after doing the succinylation. I read a lot of paper, they show, oh, you do succinylation, you get a better gelation and so on. The paper shows it doesn't do a good gelation. And this is the same paper, they also show that foaming properties are compromised. I really enjoyed reading this paper because they openly tell it's not necessarily good. It might be super bad, right? So always keep in one thing in mind, modification not necessarily change things in a positive direction. It can also compromise negative direction. So when you become a PhD student, you have to try different modification, and one might work. And that working one might not improve everything. It might decrease something, it might improve something. So you have to keep in mind that I'm not claiming here that the modification will always improve the techno-functional property. They can also have a negative consequences. Okay. And we can also use polyphenols to modify proteins, because when polyphenols attaches to protein, it's a fake polyphenol. Imagine it should be a 6-membered ring. I'm showing 5-membered ring here, and sorry about it. You get more and more hydroxyl group and more hydrogen bonding, more and more polar residue. It can change the solubility. And people are also using nowadays polyphenols to modify proteins. Okay, but it will also change the color, just to let you know. Am I clear? So there's a lot of way to modify techno-functional properties of proteins. The first one is we're going to talk about the most important experiment. The thing we do nowadays is using transglutaminase. It's an enzyme to modify proteins. Transglutaminase is an enzyme that will cross-link two proteins. Basically, it will cross-link glutamine residues with the lysine residues. Now imagine you have two protein, one with the glutamine and another with the lysine, right? Then if you add an enzyme called transglutaminase, it will cross-link these two residues and you get a new protein where two things are cross-linked. Am I clear? Originally, they were individual proteins. Now you are combining them covalently by adding an enzyme called transglutaminase. It will transglutaminate, that means it will combine or cross-link or covalent reaction it will induce, that is combination of glutamine and lysine residues. Please note it's a covalent modification, that means it's strong. Now can you think a little bit about why need to we do the cross-linking? What is help? What it will benefit? It will improve the texture, because sometimes we need this texture, we need an extra complicated gelation, right? And that can be done with transglutaminase. Am I clear? Please note that transglutaminase also have other chemical properties. It can also do acyl transfer. This is the I just mentioned. It can also do the deamidation, that we will do it later. Just for now, just remember it can cross-link two proteins together. It can also cross-link multiple protein together doing intermolecular transglutamination, intermolecular reaction. When it does an intermolecular cross-linking, then you get a new structure. Multiple proteins can be cross-linked together. They were individually like this one. Now they cross-link each other and you get a new structure, intermolecular cross-linking of protein. It's a very important reaction. It gives a fantastic functional properties. Let's take as an example here. These guys were trying to prepare a pea protein based bagel, and you can see that when they increase the content of transglutaminase, the hardness is increasing, right? Now you can see it's very soft here, right? Now they're getting more hard and hard gels, and that has a different functional property. It's very important to get hard gel in many cases. Let's take an example here as a cheese. Now they are creating cheesy structure using transglutaminase. Now on the structure on the left, in the right is without transglutaminase. You can see clearly here, it is more powdery in nature, more brittle in nature. Now if you look into this part here, you can see how nice, how compact it is. Cheese has to be having a cheesy structure, right? You have all eaten cheese, right? Paneer, for example. If the paneer is very soft and liquidy, do you like it? It has to be hard. And that hardness can be created by creating this protein network. And transglutaminase does that particular job. Am I clear? And you're going to have a last day on exclusive lecture how we can create plant-based cheese using transglutaminase. So I don't cover it in detail today. Is it okay? There will be somebody coming on the last day of the GAN program. That person will talk a lot about how we can use transglutaminase to create a structure. Basically, it will help cross-linking multiple proteins together. It will cross-link glutamine and lysine residues, and that gives you a condensed structure, and that gives you a new texture to the protein. People are using a lot today to create cheese using transglutaminase. Okay. Here is an example that is a real meat sausage. They used transglutaminase. You can look in the texture here. This texture is very different than this texture. It's more soft and more homogeneous, more cross-linked, because the cross-linking is important, because when you tear off meat, and that fibrous structure is very important, and that fibrous structure comes because of protein-protein cross-linking. And here you can clearly see soy protein isolate without cross-linking and with the cross-link is having more hardness here. Now you can see more clearly here. Soy protein is concentrated. The fibrous is less compared to here with transglutaminase. So adding transglutaminase actually improving the texture, the fibrous nature of the protein because of this entire cross-linked network. Am I clear? So this is something used in real life in food industries. So there are companies, they sell transglutaminase in bulk. You can use to create new textures. A fantastic enzymatic reaction to do if you want a fibrous structure, if you want a gel. Okay. And then we have another enzyme called tyrosinase. Transglutaminase will cross-link glutamine and lysine residues. Tyrosinase will cross-link two tyrosine residues. You have a tyrosine. This is tyrosine. Okay. If you had an enzyme called tyrosinase, it will oxidize tyrosine into a compound called a electrophilic compound, something like this one. Okay, quinone, right? And when the quinone is formed, basically it can react with a lysine residue like this, coming from another protein. Then you get a lysine tyrosine cross-link. Okay, a lysine tyrosine cross. Basically, now two proteins are cross-linked now. In addition to that, in another pathway, it can form two tyrosines can be linked like this. Just to give a fake structure, two tyrosines can be linked. This again makes the cross-linking. Basically, one protein is cross-linking with the other protein using tyrosine residues. As I mentioned previously, cross-linking will help you get the gelation, right? People are trying to use, now you can see that in this case they are using tyrosinase enzyme here. In oat protein isolate, they get a more aggregates here. Can you see? So to create aggregates, you can use tyrosinase. Aggregation, if you have an extensive aggregation, you can get a gelation. Gels are very important to get a cheesy structure, to get a meaty structure. So you can use enzymes to get that structure. Am I clear? Then I'll take the last one, partial protein hydrolysis. Basically, in this case, you have a protein. It might have a different property. So it might be having a lower solubility. Now you can use the protease enzyme. There's a lot of commercial proteases are available. You can convert them into polypeptide. Okay. Now, the partial protein hydrolysis will help unfolding of the protein. It will reduce the particle size. It will reduce the protein size, and all these things will improve the protein digestibility or functional properties. Am I clear? In the previous case, we are actually creating bigger structure. In this case, we are breaking the protein to get a small particles, and sometimes they improve the solubility, someday they will improve the gelation properties. Why? Because now because of the hydrolysis, protein will be unfolded. When the protein unfolds, they interact with other proteins nicely, and they can create more gelation, more aggregation. So for the partial protein hydrolysis, we are using proteases. Any question here? Is basically breaking the protein into smaller pieces. Please note that we use the word partial. That means we are not completely hydrolyzing the protein like we did it in our previous lecture. That's complete hydrolysis. But in this case, we don't do complete hydrolysis. We are only partially hydrolyzing the protein. We're talking about 1%. We're talking about 2%. We're talking about 0.1% hydrolysis of protein, not 100% hydrolysis. A small hydrolysis of protein can lead to protein structural change, and that will lead to protein functional change. And I will talk, there is hundreds of different articles about partial protein hydrolysis and improving the gelation, foaming, and everything. I don't cover them because I already taught you all these things. I'll tell you a little bit beyond that what we can get. Here in this study, they use partial protein hydrolysis. You can see they get the more umami flavor. So partial protein hydrolysis can be used to improve the flavor properties. Umami flavor is very important to get a meaty structure, meaty flavor. But they're also getting more and bitterness. Can you see here? It's a disadvantage. Why? Because when you hydrolyze proteins, you do protease. When you hydrolyze them, you get a peptides, small peptides. Peptides will have taste. Peptides will have taste. Okay? Some peptides are bitter in taste. That's not good. Some peptides are umami in nature. Some you know about kokumi peptides, there's a lot of research going on. They are dry peptides. Basically, they give you the meaty texture in your mouth. So you can use partial hydrolysis to get this meaty flavor in your mouth. but it has to be very balanced. Why? Because when you do a partial hydrolysis, sometimes you get bitterness, sometimes you get kokumi, sometimes you get umami. It's all mixture. If you really want to get one taste, you need to purify them further. It's not easy because you have a mixture of 100 different type of peptides. How do you purify them? Again, you need to use a purification strategy here. And I think Asta was talking about bioactive peptides in one of the lectures, right? You can also get bioactive peptides using partial hydrolysis. But again, purification is a challenge. You need to purify the bioactive peptides out of 1 million other peptides. It's a challenge, but you can cleave them partially to get the peptides of different properties, anti-inflammatory, antioxidant, and whatnot, and also flavor active peptides. Is it clear? Partial hydrolysis? Any question about partial hydrolysis? Partial hydrolysis is nothing but we use proteases to partially cleave the protein, and that will give you new functional properties. Foaming, gelation, it's always there. It can also create flavor because peptides will carry flavor properties. Okay. One last thing I'll try to cover is deamidation. It's again another enzyme we use, glutaminase. You remember my phosphorylation lecture? You converted some succinylation, for example. You converted positive into negative, right? But there we use chemicals. You can also use enzymes to do their job. For example, if you use an enzyme called glutaminase, it will convert the glutamine into glutamic acid. Okay? And now this was positive, now it becomes negative. So protein gets more and more negative charge when you use glutaminase. Basically, the surface charge is changed, functionality is changed, solubility is changed. This already I have explained. So glutaminase can also be used to change the surface charge. This is one example I have shown you here. You can see that by glutamination, you can increase the solubility of the protein. You can reduce the particle size of the protein. Changing the solubility, changing the particle size will change the functional properties of protein. And that brings to the end of my today's lecture.